Let's talk momentum. Now remember, okay, let's do this. We said we were talking about firemen jumping out of a building. All right. Let's say a fireman jumps out of a second-story window. Okay, fireman jumps out of a second-story window. How high is the second-story window?
2 stories.
How high?
Looks like he jumped off the roof.
Okay, let's say the roof then. How high is 1 story?
10 meters.
10 feet? How many meters is that? And say approximately 3? Okay, so let's say this is 6 meters. All right, so tell me, right before the person hits the ground, what's their momentum? So, momentum right before they hit the ground. Everybody go.
What about their mass?
Ooh, we need more information. So how about we give you their mass? Let's say that they're all suited up and everything, so they're going to be pretty heavy. So let's say 100 kilograms. That's about 220 pounds. So even for... That's right, so they're wearing all their Ghostbuster equipment. So 220 pounds. What's their momentum right before they strike the ground? Go. Okay, what methods do we have to solve this? First of all, I asked for momentum, right? Very good. Mass times velocity. Mass, check. Got it. Velocity, no. How do we find velocity? Wait. Back up. What kind of physics helps you find the velocity? Kinematics or conservation of energy? Either one. If you choose kinematics, and many of you have chosen kinematics because we just covered that, you would say, well, it starts with an initial velocity of 0. You probably call down positive. The acceleration is 9.8 meters per second squared. And we know how far the person is falling, starting from 0, landing at 6 meters. And so you're probably going to use which equation? X equals x naught plus v naught t plus 1/2 at squared. That one?
Yeah.
Solve for... No, you don't know the time. How do you solve it? How about v squared equals v naught squared plus 2ax minus x naught? Very nice.
That's what I did.
And that is 0, and that is 0. And so your final velocity is 2gx square root, where x is 6 and g is 9.8. Now, for those of you that decided to use energy, you said, well, I'm starting with, well, first of all, can I use conservation of energy?
Yes. Energy's always conserved.
No, well, energy is always conserved, but you may not be able to use conservation of energy in an equation form because it may be turning into a type of energy you can't account for. So we can account for all the energy we start with and what we end with, and we know that we only have our conservative forces acting on it, right? So we have potential to start, and we end with only kinetics. So mgh equals 1/2 mv squared. That cancels, and I get v equals 2gh square root, and we have the same. So what's our velocity that we land with? 10.8 meters per second-ish. So our momentum is 1084. We'll do 1080. We'll round it. 1080 what?
Kilograms,
1080 momentum.
Kilograms,
No.
Kilograms per meter squared.
Kilogram times meters per second. There you go. Kilogram meters per second. There is no special unit for that. That's it. That is our momentum. Okay, now, next question is, the firefighter has that momentum before they hit the ground. What's their momentum after they hit the ground?
0.
We'll go to 0, right?
Yeah.
Okay, so initial momentum is 1080 kilogram meters per second. Final momentum is 0. Okay, so here, everybody, what's my change in momentum?
Negative 1080.
Because literally it is final minus initial, so I'm going to get a negative 1080 kilogram meters per second. Okay, now, what impulse is required on the firefighter to bring them to rest then? Well, yeah, because an impulse equals the change in momentum. So it's going to be 1080, but negative kilogram meters per second. Okay, there is our change in momentum right there. That's our impulse as well. But impulse equals F delta T, right? So what's the significance? What's the significance of this negative sign here then?
Negative force.
That means that force is what direction?
Opposite of what's positive.
Yeah, opposite of what we were calling positive. Which way were we calling positive?
Down.
We were calling down positive. So this is in the opposite direction of what we were calling positive. So that means the force from the ground has to be up. Does that make sense? But yeah, if you hit the ground, the force is going to push you up. What would happen if the force pushes you down when you hit the ground?
Accelerate.
That's right. You'd accelerate down. All right. All right, you'd accelerate more down, which won't happen. Okay, now let's say this is a brand new firefighter, doesn't know what they're doing, jump out the window, and he hits the ground like this, with knees locked. Okay, about how much time do you think that takes to stop?
Very quick.
0 seconds.
Okay, with knees locked, your time to stop will be quite short. Less than a second? Tenth of a second?
Definitely less.
Okay, how about we say a tenth of a second? We say a tenth of a second then. What force does the ground apply to this person?
Greater force than before.
10,000.
Yeah, you divide this by 0.1 and you get 10,800
Opposite direction.
newtons in the opposite direction of the way you were falling. Ouch! Okay, that's bone-breaking force. Okay, so what if the fireman knows better? Okay, and flexes when they fall. How much time do you think it takes?
2 seconds. No way.
Probably not a couple of seconds, probably more than half a second maybe. Well, and another thing that's true too is remember when the fireman does that, they don't actually come to a complete stop, right? So their change in momentum will be less. Okay? So let's just say it takes them a second. If it takes them a second, then what's the force? It's just 1,080, 10 times less. Okay, what if they hit an airbag? Like they jump into a big airbag. Takes them a couple seconds. Shoot, you can do that all day, right? 400 newtons of force on you, as long as you don't land straight on your neck. Okay, you're fine. Okay? No big deal. Okay, because, by the way, what's that? All right, so what happens is 500, if it takes 2 seconds, like you hit an airbag, it's going to be about 500 newtons of force, right? 500 newtons of force is not very much. That's, Newton is about takes about 4.5 newtons to make 1 pound. So you're talking, 100
How many newtons
plus
does it
pounds.
take to make
Baseball bats.
God won't allow that to happen.
Why do you want your baseball bat
God does it.
to be hard and not spongy?
Because the time.
Why do you not want to go up there with a Nerf bat?
Because it'll make the acceleration great.
Because if you have a soft bat, it's going to absorb the energy.
Okay, we're not talking energy here. We're talking momentum and impulse.
We want it decreased out, so therefore.
Very nice. We want to decrease the time of contact,
Force is great.
thereby increasing the force. What happens is when a ball hits a spongy bat, the ball slows down over a greater period of time. Therefore, the force from the bat on the ball is less, so the ball cannot travel as far. Okay? Can't travel nearly as far. But if you hit it with like a metal bat, it's much easier to make the ball go farther with a metal bat than it is a wood bat even. You want to what? You want to hit a ball now? Okay, yeah, everybody get a baseball bat and hit like a softball, because the softballs flex more. The softball doesn't fly as far for a couple of reasons. Number one is because it's bigger, has more air resistance. Number two is it has a little bit more mass sometimes, so it's harder for you to hit it out. And three, it's softer, literally is softer, so therefore it won't fly as far because it absorbs more, longer time of contact, less net force on it, so therefore it doesn't fly as far. A baseball will fly farther because it's harder. And if you really want to make something fly far, hit a golf ball. Okay, because a golf ball is really hard. Golf ball will go a lot farther than a baseball will. Yeah, because it's more rigid. It's springier, and so the time of contact is shorter. So the force is greater. It is harder to hit. Right, it's hard to hit. Or you hit a super ball. You know what a super ball is, right? Like rubber balls. Those suckers will fly a long way.
Why?
You won't
They're
get that
soft.
back. But they're springy.
Oh, okay.
They actually bounce, so they'll go real far. So, anyway, all right. So there you go. That's impulse and momentum. All right. So let's talk another thing about impulse and momentum real quick. Let's say that you would like to go to space. All right. So you get in your handy dandy rocket. Someone watched Blue's Clues when they were growing up.
I just found out it was a girl. I was so disappointed.
Who was a girl?
Oh, I thought that was
Blue's always been a girl.
And they make the pink.
I know, they make the pink for the guy. What's that supposed to
Come
be?
on now. That's not
I was so upset.
You gotta realize.
All right.
Yes.
Now, you are going into space. All right. So here you are going into space. How does a rocket go into space? I know, like that. But a little more physics
With
detail,
impulse.
please. Yeah. There's a rumbling sound, and then it goes up. Very nice.
You
Thanks,
fire
guys.
things up and then it goes kaboom and then.
You fire things off, it goes kaboom, and it goes up. Can you talk to me physics? What does that mean?
Kaboom.
It up.
Pushes the force against the ground, pushing it upward.
Okay, does the rocket push against the ground
Well,
to go up?
do you...
What
What about that rocket that's already in space? Reaches down to the ground and pushes
It
off?
doesn't.
Momentum.
You don't use any of that when you're in space. It just continues. You don't even use anything to
Constantly
keep
increase your
going.
momentum.
All right. When a rocket fires off, what comes out the tail end?
Fire.
Fire.
And smoke.
Yeah, that fire is shooting stuff out the back, right? Okay. What you have is a very fast chemical reaction. What? So here we are. Here's our rocket. Our rocket is sitting here. Our rocket, to fire off and launch into space, stuff comes out the bottom.
That's a very limpy roll.
Sideways.
Yeah, it's launching to space. All right? Here, launching to space. Fire comes out the bottom. Shh, come on. Fire comes out the bottom. Fire, but that's a very fast chemical reaction producing a hot gas that's expanding and shoots out the bottom. So as it shoots out the bottom, the gas exerts a force on the rocket, making the rocket go up. And the rocket is pushing the gas downward. For every force, there is an equal but opposite direction force. So the rocket pushes the gas down, the gas pushes the rocket up. So how fast does the gas come out the bottom compared to how fast the rocket goes up?
Goes down
It
a lot
comes out
faster.
faster.
Why does it come out a lot faster?
Because it doesn't weigh nearly as much as the rocket.
Because gas molecules have very small mass. Rocket is very heavy. So the rocket takes a long time for the rocket to build up speed as this stuff is firing out the backside. Okay? By the way, remember when we talked about gases and thermodynamics and all that? The special property of gases that made them so special
Yeah.
was that they could expand, right? That's why we shoot rockets into space using expanding gases, because they can expand. As they expand, they exert a force on the bottom side of the rocket, shooting the thing upward. Okay, so for every force, there's an equal and opposite force. Okay? Now, let's talk about that for just a second. Okay, we're going to expand that idea. All right, here we go. Cue ball, 8 ball. Okay, we're at the end of the game. You're trying to call your shot. Put the 8 ball in the pocket. All right, here we go. Cue ball comes along. Contacts the 8 ball. Okay, you ready? Got some really tough questions for you. Okay, the force from the cue ball on the 8 ball. How does that compare to the force from the 8 ball on the cue ball?
In opposite direction.
Who said greater? For shame. They are equal and opposite. Okay, now, equal in magnitude but opposite in direction, right?
Yep.
Okay. Do you really believe that?
No.
No?
Friction.
Why don't you believe it?
Because it sounds
The
stupid.
cue ball doesn't fly as
The
far
cue
that way
ball
as the
stops.
8 ball.
Oh, because when you hit, because yeah, that's because you take the force
Depends on
to change
final
its
velocity.
Because when
Yeah,
you
hang on, one at a time, one at a time. Why don't you believe it? You said no? Who said no?
It makes perfect sense.
Why don't you believe it?
because when you play pool
Yeah, Jonathan.
and you hit it, the wipeout doesn't move as far.
That's because
That
it takes
depends on
force to
velocity.
change
Both
its
ways
momentum
it's-
from positive to 0.
But, okay. Cue ball hits 8
The
ball.
force is the same.
If the force is exactly the same,
The cue ball would stand still, another would go at the
they have the exact same mass, right?
Because
So the force on the 8 ball, what does it do to the 8 ball? Makes the ball accelerate that way, right?
Unless
If
you
it was
miss it.
perfect, then it would be going at the same speed the cue ball was going.
And
The cue
the
ball
cue
would
ball
stay
stays still.
exactly still.
And if this one, the force on this one makes it accelerate that way, right? And those two forces cause exactly the same acceleration on exactly the same mass object, right? So F equals ma. They have the same mass, and if it's the same force, they should have the same, but in opposite direction accelerations, because the forces are in opposite directions, right? So, if the force is big enough to bring this one to rest, then this one should take off with the same velocity that this one had. Does that make sense? Does that happen?
Why doesn't it just...
It does if you hit it right.
Yeah, sometimes you can hit stop and then the other.
never.
Yeah, if you hit it right, it will do that. Okay? Now, but wait a minute. There are other examples on why people don't believe Newton's third law. What are other reasons? Like, for instance, you're driving down the road, your car hits a mosquito. Which gets the bigger force, the car or the mosquito?
Well,
Is it
they
proportional?
get the same force.
It's the
same
same
as the mass.
force. Why does the mosquito lose?
Because its mass is so
Because
small.
it has a tiny mass, right?
Unless
It's a tiny mass. What if you hit a mosquito the size of a bus?
You lose.
Then you'd lose,
That's your favorite mosquito.
right? Because you have less mass, right?
They go to the sides fly.
Mosquito.
Okay, you must believe Newton's third law. For every force, there's an equal and opposite force. Go running around the hallway, running into things. Believe me, every time you run into something and apply a force to it, that thing's going to apply a force back to you. Right? Yeah, like that. Exactly like that. Why do boxers wear gloves?
Because it hurts if you hit someone in the face.
Yeah, you can break your wrist. I mean, break your knuckles.
Yeah.
Exactly.
Where's the bullet?
That's right. Yeah, that's right.
Don't listen.
Come here, let me show. All right, now here we go. You've got to believe. Okay, the force from the cue ball and the 8-ball. Force from the 8-ball and the cue ball. They are exactly the same, but in opposite directions. Okay, now I got a really challenging philosophical question for you. How does the time that the cue ball is in contact with the 8-ball compare to the time that the 8-ball is in contact with the cue ball?
One's greater than the other, definitely. Can't
They're pretty much
That doesn't.
Same.
That question doesn't even make sense. Like
It does.
you're saying, like how long is this and touching that and that touching this?
That's the
Same.
point, Ian.
That's so dumb. It's,
Here, let me prove it.
ah.
No, it's the same.
It's got to be the same, right?
They're touching.
So wait a minute. Wait. The time is the same.
The impulse is
Velocity.
Yeah.
So how is the impulse?
the impulse is
How's the impulse on the cue ball and the impulse on the 8-ball? How do they compare?
Impulse.
They're exactly the same. This one gets an impulse this way. This one gets an impulse this way. This impulse stops the cue ball. This impulse makes the 8-ball go. Okay, now wait. Here's the big kicker. Well, not quite yet. How does the change in momentum of the cue ball compare to the change in momentum of the 8-ball? They're almost the same. How are they different?
opposite direction.
Opposite directions. So one of these is positive. This one gets a positive force and impulse. This one gets a negative force and impulse. This one has a positive change in momentum. This one has a negative change in momentum. Okay, now, wait. Here's the kicker. How does the impulse of the system change? Back up. How does the change in momentum, what is the total change in momentum of the system?
Zero.
There we go. I know I could word it right.
There's no change in momentum.
Do you see that the change in momentum of each ball is equal and opposite? Therefore, when you add up everything that's interacting, that the total momentum change of the system is 0. It has to be 0. Okay, let's go back to our rocket.
Do you have tissue?
All right, so here we go. Everybody? Does the rocket receive a force? Yes. Upward. Force on rocket. Does the gas receive a force?
Yes.
How big is it? Same as that one, but downward. Oops, on the gas. All right, wait a minute. Does the rocket receive an impulse? Does the gas receive an impulse? How do they compare? They're the same, but in opposite directions. So they have the exact same impulse, but one's up and one's down. So do they both have a change in momentum? Except this one has a change in momentum that's up, and the gas has a change in momentum that's down. Okay, now what's the change in momentum of the system? 0. It has to be 0. Okay? Has to be 0. Now we will prove this in Physics C next year, but this also means that the center of mass of the system never changes location. It always stays in the same spot.
Relative
Relative to some location you're measuring it from. So like if this is the center of mass of the system, as the rocket goes up, the gas is going down, the center of mass of the system stays in the same spot. We'll prove that next year. In fact, we just kind of did that today in Physics C. All right, everybody, this is the really, really cool thing right here. This is what really makes momentum worthwhile, is this idea that you have equal and opposite forces for equal time, therefore equal and opposite impulses, therefore equal and opposite changing momentums, therefore if you keep track of all the objects interacting, the change in momentum of the system is always going to be 0. So
us walking?
So you walking, okay? You're walking on the floor, so you're interacting with the floor. So you're moving that way, so which way should the floor move?
Yeah.
That way. So why doesn't the floor move that way?
It is very.
It's small amounts.
Very slightly.
Has a huge mass, so it has a small.
Somebody over there is walking the other direction.
All right, there's several reasons. Reason number 1 is you're standing here walking that way. Now, if you were on a skateboard and you jumped that way, what would the skateboard do?
Go the other way.
Go the other way. How many of you have ever been in a boat and you jumped from the boat to the dock? Yes. And you realize really quickly that you have to jump a lot farther than you thought, because as you jump forward, the boat goes backwards and you can miss the dock. Okay?
So you can hit your face.
Now, if you're on a big cruise ship and you jump off the cruise ship to the dock, do you have to worry about it then?
No.
Why not?
0.1.
It's if you get
Because the other is a huge mass. So what's its acceleration going to be like? Very small. So when you walk across the room like this, you're pushing the Earth back that way. So why don't we notice the Earth going backwards?
Because it's spring.
No, because
huge.
you have a minuscule mass compared to the Earth.
what if everybody
Oh,
was
yeah.
walking that
What
way?
if that?
Now,
Get Richard out here.
That way.
Everybody go to the east.
that's right. Which the Earth rotates to the east, right? So let's say we wanted to stop the Earth. We would have to run east, and we'd slow the Earth down, right?
Wait, could that be possible if we got everybody on the Earth to run the same direction at the
I
same
don't think
time?
their mass is enough.
Until we ran into the ocean.
I don't know.
Well, just like run in place.
No, their mass is enough.
You can't run in place. It's like a treadmill.
Rudy, there's not enough mass with all the people.
Rudy, that's one of the silliest things I've
What
ever
if we got all the
Like
animals
6
to do it
billion
too?
All right.
Buildings.
Actually, okay, here.
6 billion people times what?
Swim
150 pounds?
Okay, somebody get on the internet, find out what the mass of the Earth is.
And then figure out the mass of all the people on Earth.
All right. What's the mass of an average person? That's right. American, European are normal.
Well, see, China and India make up for like a third of the world's
Okay,
population.
let's make it easy, because we'll just get order of magnitude. Let's say everybody's 100 kilograms. That's really hefty.
Yeah.
For average, that's really hefty. But just so we have a number, okay? And how many people? 6 billion?
Actually, it's getting closer to 7.
Okay, let's say 7 billion.
Something about.
Times 7 times 10 to the
Billion.
10 to the billion. How many is that?
That's
9.
9.
All right.
Wait.
All right, so that's going to be 7 times 10 to the 11th kilograms worth of people.
The mass of the Earth is 5.9742 times 10 to the 24 kilograms.
5.97
42.
times 10 to the what?
24.
24th kilograms. All right, so if we get everybody on Earth running in one direction along the equator, trying to slow the Earth down, will we notice it? No, because look, we are so many orders of magnitude too small to matter.
What about all the
What
animals?
are, yeah, the animals
Buildings, if you put like
Still
and the
would.
whales.
Everybody get in their car, everybody get in their Hummer and drive east.
What if we just make one big bridge across the equator?
Still no.
Everybody
Yeah.
drive.
Anything on the surface of the earth is also
But
into the whole.
1124. There's 15 more zeros in there. That
Every person
Tell us
in the
no.
world has got an 18 stuffed it with like bears.
And then still wouldn't work.
All right. So, here's the deal. We can't really affect the Earth in a measurable way, right?
What if we're going really fast?
Now, if you held the moon on your back and ran east, then maybe we would see a difference. What we just derived is what's called conservation of momentum. Here are the rules. Okay? Here are the rules for conservation of momentum. Is if you have objects that are interacting, okay, like exerting forces on each other, then you must include all of the objects that are interacting. Because you have to account for each and every interacting impulse. So that you can add up all the interacting momentums. So therefore, they'll always add up to 0. Because this always adds up to 0. As long as you can include everything that's interacting. So let me give you a few examples. Okay? You're on a skateboard. You jump that way. Okay? What object are you interacting with? Skateboard. Okay, so you're interacting with the skateboard. So you have to include the skateboard in your problem. So you'll jump that way, the skateboard will go that way. So there's no change in momentum of the system. Okay, you run down the hallway, you run into another person who collides with another person. How many objects do you have to include in your problem? 3. Okay? All right. What if you run down the hallway and run into the wall? How many objects are interacting? 2. Can you use conservation of momentum for that? Why not?
Oh, because the wall doesn't move.
Yeah, because the wall is attached to the Earth and there's no real way for us to include the Earth in our problem, right? Okay? We can't really include the Earth because the Earth is not, we can't really include it. We can't measure what it's going to do, right? You have to be able to have objects that are interacting and that are free to move otherwise, okay? All right. So if that is the case, then we have conservation of momentum. All right, so here you are. Here's your balls all ready to break here.
Yeah,
It's a
you
really
went
small pool table.
You went one too far.
Nuh-uh, there's 15. And 8 balls right here.
They're just really big in comparison to the table.
Yeah, they are. It's a junior table.
With a dull ball.
Yeah. Here's the cue ball. Okay, why is it so important to hit the cue ball really hard when you're going to break?
Its mass is so small compared to theirs.
Because all these are the same mass, and this starts off then with a momentum. This ball hits these. After the collision, what's the moment? We have all these 15 balls plus the cue ball, 16 total, interacting. I have to include all of them. But when I include them all, and I add up the momentum of all of them afterwards, what will be their final momentum afterwards? Not 0.
115?
116 of the original.
115.
Negative that.
It will be this. Will it be the negative of this? Will the whole thing shift this way? It's all going to shift this way, right? And so afterwards, the momentum of this entire batch is going to be this way, and the final momentum will equal the initial momentum. And so if you hit this really slow, then this momentum will be split up amongst all of these, and they're not going to go very far, right? It's going to be split up among 16. So you have to hit it really hard, and then all these will take off. Right? And they'll take off, if you add them all together, they'll all go in this general direction. Now some of them take off this way and that way, but when you add all their motion together, guess what? It's that way. The same direction that this was. Okay? Same exact direction. All right, so here, let me ask you this. Let's say that here's a car. This car is coming along. It hits this car. Actually, I need to look at this from the top so it makes more sense. So here's a car. Ooh, it's a limo. And it hits a... hits another car going this way. All right?
Now, which one is breaking the law?
Which one's breaking the law? Let's say the limo. They're not paying attention. They're driving really fast. This one's driving slow. This one has a mass. This one has a bigger mass, say. All right, when they collide, if they collide and stick together, which way do they have to go?
The same.
Diagonally.
Diagonally, which way?
Well, it depends on whatever.
Up and over.
Into the first quadrant, right? Up and over. Okay, here's the deal. Does this one have momentum?
Yeah.
Which way is its momentum?
That way.
This way. It's a vector, right?
Yeah.
Which way is this one's momentum?
North.
North. So the total momentum of the system, everybody,
Remains.
is that plus that before. So there is the net momentum. There is the sum of the momentums right there. That's before. So afterwards, what has to happen? This is our initial momentum. This way. So after the collision, if they hit and stick together, they've got to go off this way. They have to. Okay?
Yes, sir.
Okay, so here's a question they'll give you on the test. Here's the 8 ball sitting here. Here's a cue ball. The cue ball comes in and slices off that way because it hits off center. Okay, which way does the 8 ball go? Does it go A, B, C, D, or E?
It's not C, not E, because you're trying to figure out a place to put E, but it's C, because it has to cancel out the other side.
I say C.
It's C.
Which one?
C.
C. Why is it C?
Perpendicular with half of the ball. I mean,
Does it have to be C?
Yes.
Like
It'd
exactly.
be C and a half.
Most likely.
But it's most likely in that general.
Most likely, because here's the deal. Here is our momentum afterwards. Here is our momentum afterwards here. Notice that our original momentum was this way. So our final momentum must be that way. So what has to happen to this y momentum this way and this way? They must cancel out. And what about this x momentum and x momentum here afterwards? They must add up to the original. So that afterwards our momentum is exactly the same as we started.
Yeah.
All right? Excellent. All right, we have, count them, four different types of collisions. Types of collisions, here you go. There are 4. You ready? They are, in order, explosion, elastic,
Elastic.
inelastic,
Perfectly in line.
and perfectly or completely inelastic.
Or elastic.
Now, there are some books that will word these slightly different. Sometimes books will call this one, possibly they'll call this one inelastic. And sometimes they'll call this one partially elastic.
Yeah.
Okay? Here, when I describe them, hopefully it'll make sense. All right? What's an explosion like?
Boom.
Yeah, it's like boom. The simplest way to think of an explosion is literally to think of like a bomb. There you go.
And a bomb.
Yeah, it's a cartoon bomb. Okay, and the bomb explodes. What is the initial momentum of the system here?
Outward.
What's the initial momentum right now?
None.
0. And then afterwards, after the bomb explodes, it blows into pieces, at least 2.
Like 1,000.
It looks like an eggshell.
Kind of fun.
It's a very cartoon bomb.
A very strong bomb casing. If it
And it's
ever
even
goes bad.
still lit, so there you go.
Oh.
All right, notice that you have a negative momentum here and a positive momentum here. Hey, why do I call this negative and this positive?
Just because you defined it.
It's easier that way.
Left and right.
That's the way.
But wait a minute, if I was talking energy, I'd say this has kinetic energy and this has kinetic energy, and they'd both be positive. Why is this one negative and one positive?
Because they're different directions.
Conservation.
Okay, because momentum is a vector, right?
Yes.
Since it's a vector, direction makes a difference. So we got to be careful. It's not like energy, where all energy is energy, and positive and negative just means adding or subtracting energy. Here, positive and negative means direction. That's really important. Okay, I have a positive and a negative momentum. So what's my final momentum of the system?
0.
Still 0. But I start with, look, what's my kinetic energy to start? 0. What's my kinetic energy afterwards?
Big.
A lot.
Yeah, the answer is not 0.
Oh, right.
Okay, it's not 0 because now it has energy. Okay, wait. Didn't we just say that energy can't be created or destroyed? Where did the energy come from?
Potential
Yeah, it's coming from, like if it's a real bomb that has chemicals inside, it's coming from the chemical potential energy.
But it's not. It's a cartoon.
Okay, so our cartoon bomb, it comes from whatever's inside. Maybe it's a spring.
Because the energy came from the one the marker gave off on the whiteboard to make the
Pony poop and
Okay, the key thing is, everybody, is that this kinetic energy comes from somewhere. It comes from chemical energy. It comes from perhaps some sort of stored potential energy. Like, for instance, here is another example of an explosion. You ever seen those toys that you, oh shoot, it's the really old ones. They have a spring down here and like a suction cup, and you push the thing down to the ground and it sits there for a while, and then at random times it pops up into the air. Or the ones that you have today are these plastic hemispheres. You flip them inside out, set them on the ground, and then when somebody walks by, the thing pops off, right? Okay, the deal is it starts with 0 momentum and 0 energy and ends up with momentum and energy afterwards, right? Where did this energy come from?
the spring potential.
Originally it came from you doing work to flex it, and then it comes from the spring or elastic potential energy, right? Okay, this is an explosion as well. All right?
Cool.
So in an explosion, you start with less kinetic energy than you end up with because there's something has happened to give you extra energy. Okay? Another example of an explosion is you and your friend are at the ice skating rink. You stand next to each other and you give each other a push. One of you goes that way, one of you goes this way, and that's an explosion because you are doing work that's adding energy, right?
Yes.
All right, so there's an explosion. Here's the key thing for explosion. Momentum 1, momentum 2. Does conservation of momentum work? Yes, if you keep track of all the objects. So, yes, smiley face. Conservation of momentum works. What about energy? In energy, the final kinetic energy is greater than the initial kinetic energy. Okay? Final is greater than initial. All right. Let's talk about an elastic collision. You might want to write down, in an elastic collision, you might want to write down, this is what I refer to as a perfect bounce. A perfect bounce. In an elastic collision, the objects collide and bounce off without any loss or gain of kinetic energy. So you have conservation of momentum again, and the energy kinetic energy before and after is exactly the same. So why do I call it a perfect bounce? Well, because if you took a ball and you bounced it on the ground, if it had an elastic collision with the ground,
It would go up to
It would go up the same
it would
height,
go up to the
velocity.
exact same height that it dropped from, and it would do this forever and
Until-
ever.
Until somebody comes with a bat and hits it that way.
Okay. Now, an inelastic collision is a bounce, but it's not perfect. In an inelastic collision, you still have conservation of momentum, but you lose some kinetic energy. Your kinetic energy final is less than your starting kinetic energy. So you lose some energy. So when you take like a super ball or a golf ball and you drop it, hits the ground and bounces back up, it doesn't go up as high. That's an inelastic collision. It's lost some kinetic energy. But conservation of momentum is still good. Okay? Momentum is still conserved. You've just lost some of your kinetic energy. Where did the kinetic energy go?
Around these.
Yeah, there are a couple of primary places. If you take a golf ball and drop it, you'll hear a click, click, click sound as it hits the ground. So some of it goes off into sound and gets taken away. Some of it goes into heat. The golf ball will heat up, the ground heats up. Okay, it's like if you run into the wall, that's an inelastic collision, you're a little warmer than you were before.
Yeah.
You have to do it lots of times because you're made up of mostly water, right? And water has a high specific heat, so you have to do it a lot. But if you take a water balloon and launch it at a wall, fast enough speed, you literally can boil the water when it hits the wall.
Will the balloon pop up before?
Yeah, it probably will knock a hole in the wall too because water has such a high mass. But if you shot like a small stream of water at the wall at a high enough speed, you can make the water increase temperature. But what happens most of the time, since water has a high mass, it will knock a hole in the wall. They can use jets of water to cut holes in the wall.
That's how they cut steel, don't they, with water?
Yeah, they can.
Yeah.
They can. What they generally do though is
Avatar.
they'll put some particulates in it so it helps chop through. All right. So a non-perfect bounce. Now completely inelastic collision.
All energy.
The ball or the objects hit and they stick together. So this is where they stick when they hit. Both of these are bounces. So elastic and inelastic, they both bounce. Completely inelastic, they stick together. So you can spot those easy. Anytime something hits and sticks, it's completely inelastic. Conservation of momentum still works. And in this case, you've lost the most possible kinetic energy and still maintain conservation of momentum. You like what? Yes. They're not?
Conceded.
So, final kinetic energy zero?
The final kinetic energy won't be zero. You'll just lose as much as you possibly can and still have conservation momentum.
Yeah, because they both move together.
Yeah.
Two
So you'll
contacts.
generate the most heat in the collision, most entropy gain in that type of collision. Okay, everybody?
Yes, wait.
Somebody explain to me why we know that gas molecules in this room are having elastic collisions.
Have what? Elastic?
Elastic collisions.
Because they never stop.
Because they don't drop to the ground.
They never stop because if they stop,
It's
it's
not
not
really cold in here.
We know they're not this because when the gas molecules hit you, they don't stick to you. Because if they did stick to you, then they would coalesce into a liquid, right?
Yeah.
make you wet.
Now, at low enough temperatures, they will do this, right?
You see?
But not at this temperature. Okay, if they're inelastic, what would happen? Gas molecules floating around the room hit the wall. They lose some of their kinetic energy and slow down. And hey, wait a minute. If the gas molecules lose kinetic energy, what does that mean?
They're beginning the whole.
Yeah, they lose their temperature, right? And they cool off. And then they would slow down. And then gravity would eventually drag them all to the floor, right?
They become
So we'd have to lay on the floor to breathe.
They become water.
Okay?
Then they just become
Yeah, and eventually they would become water. They would coalesce into water or liquid of some variety, right? Or a solid maybe. Okay, so that doesn't happen. So we are forced to assume
They're elastic.
that it must be an elastic collision. All right? Now, let me give you a hint. Elastic collisions occur anytime there is a conservative force acting between the objects.
Do they actually exist?
Yes.
They do?
What, conservative forces?
No, elastic collision.
Yes. Here are the ones that always occur elastically. What are our conservative forces? Remember, we're going back. Boys, come on. What are our elastic forces? Do you remember from way back? Not elastic, I'm sorry.
Conservative.
Conservative.
Yeah.
Yeah.
They
Yeah,
are.
looking back, that's how you remember things.
That's right. We're looking back.
That's what notes.
We're remembering.
Are conservative forces?
Conservative forces.
Oh, gravity, electrostatic, and spring. My note taking is off the charts.
He doesn't think those.
You could add magnetic force to that if you wish, but we'll just stick with these three that we've talked about. Okay, gravity, electrostatic, and spring force all depend on location. Remember, the equation has a location in the equation.
R.
R or X in the case here for spring.
H for gravity.
Okay, so why do we know that, or H technically, yeah. Why do we know that gas molecules have elastic collisions as well? Because the force between them is, remember, they're electron clouds that are repelling each other, right? So they collide without actually ever touching. So they're able to have an elastic collision because they have a conservative force. Gravity forces, when objects collide due to gravity, that's a little bit harder because since gravity only attracts, when objects collide, they tend to stick together, right? With gravity. So the only way you can have a gravity collision that's elastic is if you have something odd like this. Say you have a star, and the star is moving this way, and this object is moving this way. And what happens is the star would collide like this, and this would collide like that as they go past each other. It would be an elastic collision where they don't touch. Because if they touch, they'll collide and slam together and become one bigger mass. Okay? Spring force, if you ever have a problem where you have something like this, where an object, here, like a car and another car, and this car has a springy bumper, a bumper made of a spring, and it collides with that one. What kind of collision? It will be elastic, because you have a conservative force acting between them when they collide. Okay? You can have the same thing as if you have magnets on these, where you have north facing north and they collide. That would be an elastic collision as well. All right?
So they actually do exist in the actual world?
Well, okay. In our world, even with a spring and even with magnets, we're going to get really close, but as the spring and magnets flex as they approach each other and bounce off, it does generate a little bit of heat. And so even
That's what I was going to say.
even those, it turns out that we won't be exactly elastic. We'll be close. Only when you're in the microscopic world do you get truly elastic collisions. We don't really have them in our world. We come close, but
So that doesn't exist. So this is all a lie.
that's correct. Remember, physics is the study of fewer and fewer lies. We make things really, really simple. Get rid of friction, get rid of air resistance, assume elastic collisions, and things like that so we understand the basics. And then we start adding on the more realistic situations.
Assume a sleep number of 0 will stop a car from,
That's correct. That's correct.
The softest bed ever.
All right.
And a Tempur-Pedic.
Questions on the types of collisions?
Tempur-Pedic loud.
I'm awake.
Yeah.
Hey, what if they ask you there's a car collision and they say, is the car collision elastic?
Because
Well,
it's
if the cars hit and stick together,
It's
No.
completely loud.
you say no. What if they hit and bounce? How do you tell?
It depends on how much goes.
The momentum
Yeah,
in the direction.
because the momentum will be conserved in both cases.
So it depends on
The energy.
You're just going to have to calculate the energy of the cars before and after and see if they're equal. If they're equal, it's elastic. If they're not equal, then it's inelastic. And that's the best you can do. Okay? All right, so it's time for us to look at some types of problems. We will work on 1D problems today, 1D momentum problems today, and then we will do 2D momentum problems Wednesday. Okay, let's say there's a skateboard here, and here's a kid, and a kid runs and jumps on the skateboard. Okay? All right, is momentum conserved in the y direction? Okay, we had two directions, x and y. The kid runs and jumps on the skateboard, so hits the skateboard at an angle. All right, is momentum conserved in the y direction and is momentum conserved in the x direction?
I don't know, because the skateboard's not shooting up.
Yes, because the skateboard is bending.
When would momentum not be conserved? Right?
Good question. When is momentum not conserved? Okay, remember, momentum is conserved under what conditions? Okay, momentum is conserved as long as when you have interacting objects. Do we have interacting objects? Yes. Can we keep track of all the objects? Yes. Are the objects free to move? Sort of.
Restricted by gravity.
In which direction can we have conservation of momentum and in which direction can we not? Okay, we have conservation of momentum in the x direction only, but in the y direction, we don't. Why not?
Because then P1Y of skateboard.
Yeah, because there's the earth or the floor or something there keeping it from moving freely up and down. All right? So here's the deal. In conservation of momentum, to do conservation of momentum, and when it works really great, is when you have multiple objects interacting. You can keep track of all the objects, and the objects are free to move, which means there's no net external forces on the object. Okay. The object is free to move in the x direction, but not in the y direction. There's a net force on it from the force from the ground that'll keep it from moving in the y direction. So momentum is only conserved in the x direction. So let's work this problem. Let's say, forget about the angle. Let's say the kid is running to the right at 10 meters per second. And say the mass of the kid is 50 kilograms. Let's say it's a really big skateboard with a mass of 20 kilograms. What's the final momentum? Sorry, what's the final velocity of the child skateboard system?
And the skateboard's not moving at first.
Very good. The skateboard is not moving initially. Say the initial velocity of the skateboard is 0.
So it's 5 meters per second.
Yeah.
Okay, go.
What are we finding?
The final velocity of the child skateboard system. So the child runs and lands on the skateboard and stays on the skateboard.
7.14.
What do you get?
7.14.
We got to vote for 7.14 for the final velocity.
I concur.
You concur? All right. Momentum 1 equals momentum 2. We have two objects, mv plus mv. We have the child and the skateboard. Afterwards, how many objects do we have? Yeah, you could say we have two objects moving with the same velocity, or you could say we just have one bigger object that's coalesced, right? So m child plus m skateboard and our final velocity. Now the skateboard starts off with a velocity of 0, so I can zero that one out. I end up with 50 times 10 equals 70 times velocity final. So our final velocity is 7.14. Is that correct? Excellent. Piece of cake. All right, let's say that the child now jumps off. What if the child jumps straight up and grabs onto a tree limb? Jumps straight up, grabs onto a tree limb. What will be the final velocity of the skateboard?
Where's this child's mom?
Yeah, where is this child's mother?
10, right?
Would the velocity increase or decrease?
Is he shooting straight upward?
If the child jumps straight up, what will that change the skateboard?
Nothing.
Just-
Still gonna go
yeah, it's
7.1.
just-
Skateboard will just keep going.
Oh, and then
That's
then
7,
the
right?
child will keep going, and then it'll be
Because when the
stopped by
child
the
jumps
tree.
straight up, the child is still moving forward with 7.1 meters per second, so you still have the same x momentum as before, right? If you've ever done this, you're on a skateboard, you're rolling along, you jump straight up, you go in a parabolic arc and land straight back on the skateboard, right?
Yeah.
So nothing's really changed in the x direction at all, has it?
Straight forward. Oh,
Hey, if you want to increase the speed of the skateboard, what do?
jump
You jump
backwards.
backwards. So let's say the child jumps backwards so that the child stops. Okay, so you really got to jump backwards really hard.
Yeah.
And the child totally stops himself. If the child jumps backwards and stops himself, what's the final velocity of the skateboard?
25.
25?
14.28.
Let me see. 500 divided by 20, right?
14.28.
If the child stops. Okay. Could we could do it several ways, couldn't we? We could say the momentum here at 2 equals the momentum over here at 3. So we could say m plus m, and this velocity right here would equal mv for the child plus mv for the skateboard, but the child has stopped now, right? So you could say 70 times 7.14, 70 mass, 7.14 meters per second, equals 20 for the skateboard, and the final velocity of the skateboard. What would it be?
10.
Is it 25?
I think, because I just got 500 divided by 20 instead of 500 divided by 7.
Okay, let's check something, everybody. The momentum here at the beginning equals the momentum here when they're together, equals the momentum here when the child's jumped off. So doesn't that mean the momentum at the start equals the momentum at the end? So couldn't we say that the mv of the child at the very start equals the mv of the skateboard at the very end? If we call this location 1 and 2 and 3. So couldn't we say 50 times 10 must equal 20 times the final velocity of the skateboard? So 50 times 10 is 500 divided by 20 gives you 25.
What I did.
This is amazing.
And look what's happened. We've taken the momentum of the child was combined here with the momentum of the child and the skateboard, and then transferred completely just to the skateboard. Okay, let's find out what kind of collisions these are. Okay, here's what I want you to do. What's the kinetic energy 1? What's the kinetic energy 2? And what's the kinetic energy 3? We'll do this. This table, kinetic energy 1, kinetic energy 2, kinetic energy 3. All right? Everybody calculate your part.
Of the entire system.
Of the entire system. So the kinetic energy of the system. Now, hey, before we start calculating numbers, what kind of collision do you expect this one to be from here to here?
It's completely inelastic because they're together.
Okay, it looks like completely inelastic. We're going to find out. What kind of collision does this look like?
Explosion.
Elastic or explosion? We'll find out. We'll find out. Okay, group number 1. What's your kinetic energy?
2,500.
2,500. 2,500 what? Yeah, put that unit on there. Joules. Okay. 1/2 mv squared. Right? Don't forget your 1/2. Okay, group number 2. What's our kinetic energy?
2,500.
1785-ish joules.
Yeah.
Yep.
17.
Okay, group number 3.
6,250.
6,250 joules. Yowie. Okay, from here to here, 1 to 2, does that confirm that we have at least some sort of inelastic?
Yes.
And since they stick, we know it's completely inelastic, right? Okay, from here to here, what kind is it? It's an explosion. Whoa, where did this extra energy come from?
Potential energy of the person pushing off.
Yeah, you could either say the potential energy of the person, or more likely what would be easier to say is that the person, the child, did work by pushing off the skateboard, right? They had to do work to make that happen, right? So they added energy to the skateboard. What's interesting to note is, look, the final energy at the very end is greater than the energy we started with. So work must have been done, or energy was tapped from somewhere, right? That energy was tapped from the child. The child did work to push that skateboard forward. All right? So it was an explosion. All right, so let's do another problem. All right, so let's say, here you are, this is you, this is your significant other.
Yay! That's me.
All right?
They have big
That's
heads.
weird.
They're both
They're both dudes.
Yo, man, give her.
They're stick figures.
Give Kelly the hair.
Guys.
Give Kelly the hair. There you go. Let's make Kelly.
I think I show. Oh, never mind. Never mind.
So it's,
Hey, why am I shorter? She's way shorter than me. It's her
all
hair.
right, so here you go. So it's Rudy and
Kelly.
Catalina.
Yes.
All right. So here's Rudy and Catalina. So Rudy, what's your mass, dude?
I weigh 140 pounds. So.
140 pounds, so we'll say about 70 kilograms. What's the mass of Catalina? Be careful.
I'm not going to guess 60. I'm not going to guess.
60? Okay, we'll say 60 kilograms.
Oh, you two of me.
Okay,
Just say 50.
all right. You're a good significant other. Underestimating. Excellent. All right. Now, Rudy, how fast can you run, dude?
I have no idea.
100 miles per hour.
All right, so
21 miles per hour.
That's a lot.
2 meters per second. That's pretty good.
all right, let's say your world-class sprinter can run 10 meters per second.
That's really epic.
And you haven't seen Catalina in a while, so you run and have a completely inelastic collision with Catalina. Unfortunately, you're standing near a cliff. The height of the cliff is...
90.
How long have you been dating?
90 meters. Huh?
How long have you been dating?
10 months and 25 days.
Oh my God, Brian.
So
10 months and 25 days? Wait a minute.
That's 1/4.
Wait.
He knows the hours and seconds too.
Yeah, man, I asked around.
Hey, his red cheeks because he's blushing. All right. So it's going to be 10.25 meters tall. Where do we need to place the bucket of water to cool them off?
If they fall from it's
All right. Now, where do we need to place the bucket of water to cool them off? Now, what's the dead giveaway that this is a momentum problem?
Yeah, and they're colliding, so.
The key thing is conservation of momentum is if you see objects interacting,
Which you see the scene.
okay? If the objects interact, and if they're free to move, whoa, conservation of momentum is by far the easiest way to solve those types of problems. Just like when we have an object that's falling, or, or attached to a spring or something like that, we always kind of think, wait a minute, can I solve this with energy, right? Okay. We almost out of time?
Yeah.
All right, so here's your problem. This is your homework. Turn it in next time.
Are you serious?
Yes. Copy it down.
Draw it.
Where is X? Where do we place the bucket of water to cool them off? Now, this part right here is conservation of momentum. So this is case 1, and then when they collide and stick together, this is like 1. When they stick together, that's 2. And then what happens after that? What kind of problem is it? It's trajectory motion from 2 to 3, right? So you go 1 to 2 is conservation of momentum. 2 to 3 is trajectory motion. There you go. There's your problem for next time.